I presented the theory of elementary waves at a meeting of the American Physical Society, the leading scholarly society of physicists in the world, at their meeting in Springfield College, which is the college where basketball was invented. It is fitting that I spoke during the basketball season known as March Madness. The meeting was disorganized and they had told me that I would be speaking the following day, but when I showed up to register, I was told that I would be speaking right then. So I ran over to the appropriate building and met James O'Brien, who said that I was supposed to be the third speaker. The second speaker had not shown up, and he, James O'Brien, would ad-lib and fill in until such time as I could catch my breath and get my cameras set up.
You can test the strength of an MC by how they fill time, and so since our second speaker is not here, I will step in and do it for them and tell you about some interesting physics. And Mr. Boyd, when you're set up, you can use the old hook and tell me to get off. Okay? So I will introduce myself. I'm James O'Brien again. Some of you might know me.
The MC, James O'Brien, spoke eloquently about dark matter and what we can learn about it by studying the scatter of gravity in the cosmos. I missed some of what he said because I was preoccupied with getting myself prepared. Is it possible to turn this off?
The projector off?
Yeah.
You want no projector?
No, well, I don't have my slides with me. I was told I was supposed to speak tomorrow. And I walked into registration and they said, you're on it, not at half an hour ago. So I apologize. For someone winging it, you did a magnificent job, but you have to turn it off again. There we go. The basic idea that I'm trying to present starts with the fact that there was a neutron interferometer experiment published in Physical Review in 1992 by Kaiser et al., in which they had neutrons coming down from a nuclear reactor into an interferometer, bouncing off various silicon plates and being detected down here by a detector. Where the beams split, there was an oscillating aluminum plate so that the phase of the two waves, the upper beam and the lower beam, were different. Now, so therefore what the detector saw was a sinusoidal curve. Bismuth is a metal that slows down neutrons and neutron waves. And they put a sample of bismuth in the upper pathway but not the lower pathway, varying from no bismuth to 2 millimeters to 5 millimeters to 10 to 20 millimeters. As they put more and more bismuth in, the upper wave packet was slowed down and didn't quite meet the lower wave packet properly at the exit, and so there was a decreased amount of interference. When they got to 10 or 20 millimeters of bismuth, there was no further interference. Apparently, the upper wave packet missed the boat. The lower wave packet had already departed from the interferometer. Now, they then repeated exactly the same test a second time with one small difference, which is that they put a pressed silicon analyzer crystal down in front of the detector. But that's outside the interferometer. Downstream, what this does is it decreases the scatter of neutron wavelengths and increases the peak of the Gaussian in the center so that the beam penetrates better. But you wouldn't expect that to have any profound effect on what's going on upstairs in the interferometer. But to their astonishment, they discovered that it totally restored all interference, even robust interference, at all amounts of bismuth, even 10 or 20 millimeters of bismuth up in the interferometer. There was a robust interference reported by the detector down here. They said that neither they nor the quantum mechanics could explain the results. They invoked Wheeler's smoky dragon, which is to say that sometimes weird things happen in quantum experiments and you can't predict them. Now, for a moment, I'm going to jump to another subject and come back to this one. There is widespread agreement about two contradictory facts. First, that quantum mathematics is the most powerful science that humans have ever had. And second, that there's something so weird about the quantum worldview flowing from quantum assumptions that something's got to be wrong. Everybody knows about this contradiction. Nobody knows how to solve it. But I'm going to tell you my solution, which is that sometimes there are two systems that are so symmetrical that they share the same mathematics. And perhaps quantum mechanics is on the wrong side of such a symmetry, a mirror image universe. Well, how could that be? Well, quantum mechanics assumes that wave function collapse occurs when you measure something. It assumes that there is wave-particle duality, and it assumes that waves and particles go in the same direction. There is another theory called the theory of elementary waves, TEW, which I am promoting as the basis of an alternative universe, a non-quantum assumptions universe, which has the same mathematics. Now, TEW is based on three assumptions. Number one, wave function collapse occurs before you measure something. To me, it is amazing how much debate that quantum experts have had about whether the moon exists only when we look at it or whether it exists even if nobody looks at it. TEW says wave function collapse occurs before we look at something, before we measure it. TEW claims the moon has existed for 4 billion years. Long before there were humans on Earth to look at it, the moon existed. Number two, we claim that there is no wave-particle duality. And number three, we say that we find that waves and particles, by and large, go in opposite directions. The TEW idea that waves and particles go in opposite directions helps us understand the Kaiser interferometer experiment that I spoke of a moment ago. An analyzer crystal placed in front of the detector down here profoundly changes the presence or absence of interference upstream in the interferometer. Then the analyzer crystal must be upstream from the interference. How could that be? Well, it could be if the waves were going in the other direction. If they're starting at the detector, going up into the nuclear reactor, and from time to time a neutron would follow it backwards, hit the detector, and make the whole thing visible. Now you're going to say, this is ridiculous. This has got to be zero energy waves going up that way. Everybody knows that zero energy waves can do nothing. But the fact of the matter is, you know something else that contradicts what you just said, which is that Schrodinger waves carry zero energy. They carry probability amplitudes for a Hamiltonian, but they don't carry raw energy. And yet they have a profound effect over particles because of their amplitudes. Now you're going to say, this is ridiculous. How could Schrodinger waves escape their prison in Hilbert space and be running around Cartesian space causing havoc? Well, I know how to answer that question, but I'm not going to tell you now. Now, I've come here actually today to ask for some help. I am not a physicist. I was trained in mathematics as an undergraduate, but I am a doctor. I take care of sick people. My passion is to take care of profoundly ill people with chronic illnesses. So when I send in an article reporting these ideas that I'm just presenting to you, which amounts to a paradigm shift, the APS editors take a look at it. They never heard of me. They never heard of the idea. They don't send it out for peer review, and they send it back to me and say, this is not science. I have published these ideas that I'm presenting to you a dozen times in peer-reviewed scientific journals in mathematics and physics, but not any of the journals you ever heard of. because of what I just said. So my request is this, that after I get finished jabbering away, if you guys, if you're at all interested, volunteer to serve as a blind reviewer when I submit an article on this subject to a physics journal. If you would be willing to have me write down your name and email address when I submit an article, I would appreciate getting a fair review. So, because I was told that my talk is tomorrow, and here I am, my wife is expecting me home about 20 minutes ago, so I'm going to have to leave in just a minute. I should be back tomorrow, but I can't guarantee it. My wife is very unhappy that I'm here at this time today. Are there any questions? Yes, sir.
What you said reminded me of something that I learned about maybe 55, 60 years ago in a physics course that Professor Gerald Feinberg at Columbia University taught. He introduced something called a tachyon.
There is a lot of similarity in what you're saying. What I'm speaking of are called elementary waves. They are, by other people, they're called Schrodinger waves, in which the wave goes this way and particles do the darndest thing. They go the opposite direction, and the waves come before the particle is launched. And then in a double slit, yeah, it sounds like a tachyon. In a double slit experiment, the waves come from the target screen. They interfere as they go through the two slits. They interfere at the target, at the particle gun, and then a particle at random chooses which wave to follow backwards. And this answers a question that John von Neumann couldn't figure out, which is, he said, how can the randomness get into quantum mechanics if the Schrodinger equation, which is a deterministic equation, is in control? And the answer is that from our model, there are hundreds of different Schrodinger waves, one from each point on the target screen, and the particle at random chooses which one to respond to. And we all know that particles are random. I can show in case after case that this does reproduce the same mathematics as you get with quantum mechanics, and it reproduces pretty much the same circuitry in quantum computers, but I've also been able to design, I think, a computer circuit for which quantum mechanics and TEW would predict different outcomes. But thanks for telling me that about tachyons. Reminded me a little bit of Superman, maybe. Thank you very much. Overall, I found the audience very receptive and interested and appreciative of my ideas. They said, you know, nobody understands quantum mechanics, and if you think your ideas are weird, I mean, quantum mechanics itself is weird. Someone said, I'm trying to understand the relationship between particles and energy. Matter is some kind of energy. I mean, after all, you have conservation of matter energy, and so matter can be converted into energy. In your view, what's the relationship between matter and energy? When there's a Schrodinger wave, you have an increased amplitude for something, and that must represent a particle somehow. In your theory, is energy half matter and half waves? My response was, in my theory, waves have no energy. Energy comes with the particles only. And if the energy and particles go in one direction, the waves are going in the opposite direction. He found this astonishing and difficult to understand. I find a lot of quantum mechanics difficult to understand. For example, our Master of Ceremonies, James O'Brien, was speaking about dark matter and what we can learn about it by studying gravity. And when I try to understand quantum mechanics, even the simplest things, I run into a lot of dark matter inside my own head. One person in the audience said I should not worry about not being a physicist. When Einstein came up with his great ideas, he was not a physicist. He was a clerk in a Swiss patent office. Thank you very much.
Okay, well, this concludes, unless you want me to talk more about gravity, this concludes the first section.
After I left the room, James O'Brien caught up with me and said that he was so pleased with my talk that he invited me to come and speak again the next day. Showing up unprepared at a conference and being told, by the way, your time slot for speaking started 5 minutes ago, is like being a stand-up comedian. You get to see who I really am. I found this conference very validating to me and my presentation and my ideas. I really enjoyed it, and one of the wonderful things is I think I'm going to be getting a friendship out of it. James O'Brien and I are having lunch next week.